So in this video we're going to see how the Henderson-Hasselbalch equation can be derived from the equilibrium expression for a weak acid. So to do this we start by writing down the equation for the dissociation of a weak acid, which we can do like this. So on the left hand side we have our undissociated acid, and that's in equilibrium with the dissociated acid and the base, which we represent like this. Now the equilibrium constant for this reaction we can represent with Ka is equal to, on the top line we've got the concentration of the dissociated acid multiplied by the concentration of the base, or divided by the concentration of the undissociated acid, Ha. We now need to rearrange this equation because what we're interested in is isolating H+. So first of all we need to get rid of HA on the bottom. So to do that we multiply both sides of the equation by HA, the concentration of HA. So we do the same on the other side here. Multiply by HA, concentration, so those two things cancel out. So we're left with HA multiplied by Ka equals the concentration of the dissociated acid multiplied by the concentration of the base. But we still need to get this term by itself. So now we need to divide through by A minus. Let's just write this out again here. Multiply by Ka equals H plus multiplied by A minus, and now we're going to divide through by the concentration of base, like this, and now these two terms cancel. Now we're left with the H plus concentration of dissociated acid by itself, which is what we wanted. And now we can take the logarithm of both sides, so log, and we're just going to write this side first. So I'm going to say log of H plus equals the log of Ka times HA divided by A minus. So all that together. There we go. So we've got a relationship here, so log of the concentration of the dissociated acid is equal to log of Ka times the undissociated acid divided by the concentration of the base. Now we can use one of our rules of logarithms, and the rule here is that the log of A divided by B is the same as the log of A minus the log of B, and we're going to apply that rule to this part of the relationship here. So we're going to rewrite that by saying that log H plus is equal to the log of, so we're going to take the top part of the fraction, Ka times HA, that's that part, put that in brackets there, minus the log of A minus. So what I've done there is use the rule that log A over B equals log A minus log B to transform this side of the equation into log Ka times HA, so the top, minus log A minus, so from the bottom. So our relationship now looks like this. So we've got log of H plus equals log of Ka times HA minus the log of A minus. And now we're going to use a second rule of logs, which says that log of A times B, A multiplied by B, is the same as log A plus log B. and we're going to use that rule to change the form of this expression here. Should have been a bracket in there, so we're going to expand that. So we're going to say, using these rules here, we're going to say that log Ka times Ha there is the same as writing log of Ka plus log Ha minus log of A minus, like that. So we then use another rule. So there are several rules of logs that we can use. So this time we're going to use the rule that log A minus log B equals log A over B. So in fact, this is the rule we've just seen. We're just kind of using it the other way around. So now we're going to change the form of this bit to say log of Ka plus the log of Ha, concentration of Ha over A minus, like that. So you see we've taken the log of minus log and converted it to log 1 over the other instead. So we ended up with the expression that log there is equal to log of Ka plus the log of Ha, like that. And finally, all we're going to do is multiply through by minus 1. So it goes minus log H plus, that's a plus just there, minus log A, and that becomes a minus there. Now we see in the chapter that minus log of H plus is actually equal to the pH, like that. So we can rewrite this side of the equation here. So we substitute minus log H plus for pH, and we write pH is equal to minus log Ka minus log Ha over A minus. Then we've also seen in the chapter that pKa is equal to minus log Ka. That's another relationship we see in the chapter itself. So now we can make that substitution in our equation. Find my cursor, there we go. So and then we've got pH equals pKa minus the log of Ha divided by A minus. And then finally, we'll move across. And now we're just going to write where we got to. So we've just said that pH equals to pKa. And there's one more rule of logs that we're going to make use of here. So that's where we got to. And the last rule we're going to use is that log of A divided by B is exactly the same as minus log of B over A. So you just change the sign and flip the two parts of the fraction over. So we're going to apply that to this expression here. So we're going to write that pH is equal to pKa plus log. Then we're going to flip the top and bottom of the fraction over, plus log A minus over Ha. And this equation can then be written in general form for any weak acid and its conjugate base, like this. So the pH is equal to pKa plus the log of concentration of your base divided by the concentration of your acid. And so we've gone from our initial expression right the way through to show how we end up with the Henderson-Hasselbalch equation, pH equals pKa plus the log of concentration of base divided by the concentration of the undissociated acid.